So we want to discuss one other possibility that we really haven't looked at yet, and that's the situation where an object is dual to itself, right? Because in the oriented Brauer category, we have this generating object, which we denoted up arrow, and then we added on a dual, which was down arrow. So these were two different objects. But there are lots of examples where you have a category and an object is isomorphic to its own dual, right? So we want to examine that situation. So we're going to continue to make our usual assumptions on our category, that it's rigid and symmetric monoidal and k-linear, right? So remember, rigid means it has duals, and symmetric monoidal means it has these crossings that satisfy the axioms that we discussed. So what does it mean for an object to be self-dual? Well, we've seen the notion of duality, so it's really nothing new except for the fact that it's the same object that is the dual. Right, so what that means is instead of having a cap that we would usually write oriented in one way so that we distinguish the two endpoints, one is up and one is down, we will instead now have the same object. So it goes from x tensor x to the unit, right? So we'll usually denote this by a cap that has no orientation. So you should think of both of those legs of this cap as being the object x. And then we have a cup as well, which we now don't use any orientation for. And then we have these usual zigzag identities. The only difference is there's only one object involved, and so we don't have any orientation. And so they in fact get simpler, because before, for a two-sided dual, you know, we had this and this. But these become the same when the object is self-dual, right? So we just have these two equations. And so we can define, just like we did before, we defined a universal category that had duals. That was the oriented temporally leap category. We can do the same thing, but now with an object that's self-dual, and we get the temporally leap category, which is actually more well-known. And this has one generating object. Okay, so we have this one generating object, which instead of denoting as an up arrow, I'll denote as just this sort of line. And we've got our cup and cap that satisfy these two zigzag relations that make that object self-dual, and that's it. And if we want, we can impose some condition on the categorical dimension of this object. And remember, the categorical dimension was the bubble, right? So we could say that the bubble is just d times the identity morphism of the unit object, if we want. And so we get a specialized temporally leap category. Yet in the literature, sometimes if you just look up temporally leap category, it has this extra condition. So the word specialized isn't always there, but I just wanted to distinguish between the two. So this category, what does it look like? Well, its objects are just tensor powers of this single generating object. And if you fix an n, then the endomorphism algebra, oh, for some reason I've started to call it x, this should be this line. The endomorphism algebra of that n-fold tensor power of that generating object is the temporally leap algebra, which actually came first, and maybe people are more familiar with. But the temporally leap category has a little bit more because it has endomorphisms between different tensor powers, right? And so here's an example of a morphism in the temporally leap category. We have these types of diagrams where we have strands that are connecting endpoints to the top and bottom. So this is a morphism from 6 copies of this generating object to 4 copies, just because we've got 6 endpoints at the top and 4 endpoints. Sorry, 6 endpoints at the bottom and 4 endpoints at the top. So if you require the same number of endpoints at the top and bottom, then you can compose all these things, and that's the temporally leap algebra. But altogether, they give a category. And so this has the expected universal property. The specialized version, for instance, is the free monoidal category on a self-dual object of categorical dimension d. Okay, so any category that's a monoidal category that has a self-dual object of categorical dimension D will admit a functor from this temporally leaf category. Any questions there?
This one wasn't symmetric necessarily, right?
Right, we have not, there's no crossing, so this is not symmetric monoidal category. Right. And in fact, that's the next thing we want to do. So now we want to look at a situation where an object is self-dual and how that is compatible with it also being a symmetric monoidal category. So we're going to make one simplifying assumption. So we're going to have X, this self-dual object, and we're going to make the assumption that its endomorphism algebra is just a copy of our ground field. So just multiples of the identity morphism. We made a similar assumption on the unit object before, and I justified that by saying in our applications, the unit object is the trivial module, which is a one-dimensional module, so its endomorphism algebra is just the ground field. What you should think of as a justification for this, you should think of the case where K is an algebraically closed field, and X is a simple object. And then Schur's lemma tells us that the endomorphism algebra will be the ground field. So this is also a very natural assumption, but you should just keep in mind that this X should be a simple object. Maybe we should close the door. Okay, so what can we get from the compatibility between the symmetry and this duality data? So I claim that if you take the cap and the cup and you compose them with the crossing, you get plus or minus 1, the cup and the cap back. Okay, and it's the same constant for both of them. So let's see how this works. It uses this assumption. So remember we have these zigzag relations, which I rewrote here. And we used this trick when we were proving that the functor from the oriented Brauer category to modules over the general linear group. We wanted to show that was full. There was this trick of using caps and cups to move between morphism spaces. We can do the same trick here, because we've assumed that this endomorphism space is just the ground field. Well, that's actually isomorphic to this Hom space. And the isomorphism is exactly the type of thing we did before. If we have some diagram that's got 2 strands at the bottom and nothing at the top, that's a morphism from X tensor X to the unit. Well, we can just bend one of those strands up and turn it into an endomorphism of X, right? So that gives us this map in this direction. And then we get a map in the other direction, because if we have any endomorphism of X, that's some diagram that has 1 strand coming in from the bottom and going out at the top. And we can just take that strand and bend it around, and that gives us a morphism from X tensor X to the unit. And these are inverse maps precisely because of this zigzag relation. So what that tells us is that this Hom space is one-dimensional as well, right? Because it's isomorphic as a vector space to endomorphisms of X via these maps. Okay, and well, here's something that's in that diagram's upside down, and that tells you that the crossing on top of a cup is plus or minus 1 times the cup. The only thing that's left to show is that these are the same constant, because if you look at the way we worded our lemma, it's the same alpha, right? So that's all that's left to do, and this is a little diagrammatic trick. So let's start off with alpha just times a straight strand. We use our zigzag relation to turn that straight strand into a zigzag. Now we use the fact that alpha times this cup or cap there is the crossed cap. Okay, and now we start moving some strands around. So we take this strand here and we slide it over the cup, which we know we can do in a symmetric monoidal, a rigid symmetric monoidal category. So now it's moved to here. And then we do a similar thing. We take this strand and we slide it over this cap. And now it ends up over here. And now what do we have? Now we have this cup with a crossing on top of it. Well, that's beta times the cup. And now we straighten out this zigzag again. And so we get that alpha is equal to beta. So you can see you can just play around with these string diagrams, and it's very intuitive, this type of proof. You could prove it purely algebraically with notation of just tensor product and composition, but it's much easier to visualize when you use string diagrams. Okay, any questions on this lemma that we just proved?
It's for each x, right?
For each x, that alpha could depend on x. That's right. Yeah. Okay, so that's the compatibility between symmetry and duality. It was sort of a short discussion because everything else we did in the case where the dual was not necessarily the same object still holds in this case. It's just we had this additional property that this crossing on top of a cup or cap gives you plus or minus one, that cup or cap, if we make this additional assumption on the endomorphism ring. So this is something that's new. So now we can play the same game that we played before. We can define a universal category with these properties. And so last time we spent quite a bit of time motivating the definition. So here I'm just going to skip to the definition because the motivation, the way you would come up with this is sort of the same as what we did before. And what you get is the Brauer category, which is probably even more well known maybe than the oriented Brauer category. So it's the strict monoidal, and I keep forgetting the word k-linear. K-linear category generated by a single object. We want it to be symmetric monoidal, so we have a crossing. We want this object to be self-dual, so we've got the unoriented cups and caps. This crossing has to compose to the identity. That's part of the axioms of being a symmetric monoidal category. And that crossing should be natural. So this braid relation is the fact that the crossing slides through a strand. This, we just justified why this is a natural condition. This is when we want an object that's self-dual and is simple, for instance. And we need to impose this condition that crossings slide over caps. That's in order, again, for our symmetry data to be natural, that these caps slide through crossings. We didn't need that in the oriented Brauer category, because in the oriented Brauer category, we defined the left crossing in terms of the up crossing. And then if you just attach a cap, we got this, and then you straighten out the zigzag here, you got this analog of this crossing sliding over a cap for free from our definition. But we can't do that trick in the Brauer category because there's only one crossing. So another way of thinking about this condition that the crossing slides over a cap is that we're imposing the condition that if you take a crossing and you rotate it, you get back to crossing. So the crossing is rotation invariant. So that's another way of thinking about this condition. And you didn't need to impose any condition like that in the oriented Brauer category because you were defining things that sort of made it this way. And then we need these zigzag relations in order for this object to be self-dual. So that's that's the unoriented Brauer category. And again, we can define a specialized version where we say that the bubble is some scalar d times the identity morphism of the unit object. Okay. And again, sometimes people don't use the word specialized. They just call this the Brauer category with that parameter. Now you're paying close attention to the previous thing that we just did. If you look at this condition that the crossing under a cap is the cap, you might say, well, what about the other possibility where it's minus the cap, right? Because we proved it was plus or minus the cap. You could define a Brauer category with that relation instead of this one. But in fact, it's isomorphic to this one, because if you let B prime be the category where you have that relation with the minus sign, it's isomorphic to the Brauer category defined, and your isomorphism just multiplies all the crossings by minus one. Right? So it's an isomorphic category. It doesn't really matter which one to pick. Any questions here? Yes.
Just to wrap my head around this last part. Does D change with the value of the bubble change?
Yes, that is right. D will probably change to minus D. Yeah,
and it must be somehow. My intuition is that there's a minus sign that somehow corresponds to having like an anti-symmetric form versus. Okay.
That's exactly right. And so when we discuss the applications to the orthogonal and the symplectic group, we'll exactly see this subtlety. But there are various ways to deal with it, which we'll discuss. You can take the crossing to be minus the flip, or you can move to the super world and consider it as an odd vector space. So in practice, this sign doesn't matter too much because you can always tweak something to get rid of it, basically. Other questions?
Isn't that dating just invariant in the sub? Like, I'm confused because you said the like tracing sub whatever.
Well, what I mean is if you take this map on the specialized categories, I'm pretty sure it would give you an isomorphism between these specialized categories. Oh, right. Oh, is that correct? Maybe that's not correct. No, maybe it just goes from D to D. Well, because, right, you take the cup to the cup and the cap to the cap. No, maybe just go from D to D. Yeah, you're right. But we'll see a different thing you can do to change the D to the minus D, which is the super thing.
Then I'll wait.
Yeah. Okay. Other questions? Okay, so this category has a universal property. It's the free, rigid, symmetric, monoidal, k-linear category. It's almost on a self-dual object, but let's say symmetrically self-dual. That's this relation right here, that the duality has the symmetry property that if you put a crossing underneath the cap that you get back to crossing, rather than the other choice where we take the negative sign there. And if you take the specialized version, same universal property, except you add on of categorical dimension D. And again, in your applications to representation theory, this D will be an integer because it'll be the dimension of some vector space, or maybe the negative of the dimension of that vector space. But when you define the category abstractly, it can be any element of the field. And this leads to these deleting and interpolating categories. So these categories have the usual universal properties, which I won't write down explicitly since we've seen these a few times now. But let me just draw some pictures. So objects in this specialized Brauer category are of the form the generating object tensor n for any natural number n. And a morphism looks some diagrams like these, like linear combinations of these types of diagrams. So we have unoriented strings that connect endpoints at the top and bottom, but now they can cross and you've got cups and caps. So if you have the same number of endpoints at the top and bottom, then these are called Brauer diagrams. And your endomorphism algebras are Brauer algebras. And those came first, right? So people wanted to study the analog of Schur-Val duality, but for orthogonal and symplectic groups. And they showed that the group algebra, the symmetric group, should be replaced by Brauer algebras. But they didn't, this sort of formalism of putting things together into a monoidal category wasn't really around yet, or not well understood. And so the Brauer algebras came first, and then later on, these were put together into the Brauer category.
Brauer's paper was 1937.
Right. So it's done way before. And this is the case in a lot of these things. The endomorphism algebras were studied first, and then everything was sort of souped up and enhanced to the full category later. Okay, any questions? By the way, if I didn't take the specialized version here, then your diagrams could have these bubbles floating around. Okay, why are we interested in these things? Because again, they're connected to representation theory. So let's start off with orthogonal groups. So we can take the orthogonal group, OD, over our field K, and let's let V be the natural module, so the d-dimensional vector space with your action just given by matrix multiplication. So by definition, the orthogonal group is the subgroup of the general linear group that fixes a non-degenerate symmetric bilinear form. But that's the definition of the orthogonal group, that it fixes this form. So you pick, usually you pick the standard one, like the dot product, but you can pick any non-degenerate symmetric bilinear form, and it gives you an isomorphic group. So you can see, this is going to be our cap, right? This is this bilinear form, and then our cup is going to be its dual. So we have a map going the other way from our ground field to V tensor V, and you get that by fixing an orthonormal basis. And this map is determined by where it sends the identity of the field. It sends the identity of the field to the sum over that basis of V tensor V. And you can show that this sum is independent of your choice of orthonormal basis. Right? So even though the formula involves a basis, it really is independent of that. Okay, so this bilinear form identifies V with its dual. Now, a priori, it identifies V with its dual just as a vector space. But because your O, by definition, your orthogonal group, by definition, is a subgroup that fixes this form, it also identifies it as a module over the orthogonal group. So this bilinear form is a homomorphism of modules. And so we can use our universal property of the Brauer category now to get a functor. Because this V is self-dual, it has dimension D, and this category of modules for any group is a symmetric monoidal category, which is symmetry given by the flip. So it has all the right properties, and we get a monoidal functor from the Brauer category to the category of finite dimensional modules for the orthogonal group. So in objects, it sends the generating object of the Brauer category to this natural module V. And on morphisms, it sends the crossing to our usual tensor flip. It sends the cap to the bilinear form, and it sends the cup to this dual of the bilinear form. And in fact, I wrote a little note here. It's uniquely specified by where it sends the crossing in the cap, because of this fact that we've mentioned a couple times that in duality data, once you've fixed either the cup or the cap, the other one's uniquely determined. So it's in fact uniquely defined by the fact that the crossing is sent to the flip and the cap is sent to your bilinear form. Okay, any questions there?
Yeah, but one I look at you just to make sure it means that it preserves the structure.
Yeah, now technically, some people would call this a strong monoidal functor. You have to be a little bit careful because the Brauer category is a strict monoidal category, and the category of modules for the orthogonal group is not a strict monoidal category. So by monoidal functor, it doesn't strictly commute with tensor product, but it will have this property that f of x tensor y is isomorphic to f of x tensor f of y. And then these isomorphisms have some compatibility conditions. Right, so that's what makes it fine to have a functor from a strict monoidal category to some monoidal category that's not strict. It's because we have this little bit of flexibility in the functor. Now, there is a notion of a strict monoidal functor where you require this to be a quality, but that wouldn't be true for us. Other questions? Well, because a vector space, you know, yeah.
If it was a dual, then I would agree it's only one thing.
Maybe it is strict. You always got to be a little bit careful if you're somehow identifying things. It's possible, but to be safe, I'll say it's strong. Okay, you can do a similar thing for symplectic groups, actually. So it's the same category. It's still the Brauer category that controls the representation theory of symplectic groups. So now we take the symplectic group of rank 2D, and let's let W, well, I called it W and then proceeded to call it V everywhere else. So let me call it V again, just so I don't have fewer things to change. So by definition, the symplectic group is the subgroup of the general linear group that now fixes a non-degenerate skew symmetric bilinear form. Okay, that goes from V tensor V to K. So now let's pick some basis of V. And now because this form is skew symmetric, you can't just say a dual basis. You need to specify left dual basis or right dual basis because they differ by a sign because of the skew symmetry. So let's pick a left dual basis with respect to this form. So by that, I mean this property, that if I put the V check on the left, we get this Kronecker delta. And then I'll define this omega prime, which you should think of as the dual to the skew symmetric bilinear form. It goes from the field to V tensor V. It's uniquely determined by where it sends the identity element, and it sends that to this sum over V tensor V dual. And it's important that I put the dual on the right here. So then we have a functor from this Brauer category to modules, finite dimensional modules over the symplectic group. But notice our parameter is negative, and I'll explain why that is in just one second. It sends our generating object again to this natural module. On morphisms, now it sends the crossing to minus the flip. It sends the cap to our skew symmetric bilinear form, and it sends the cup to this omega prime that we defined. Okay. And I promise I will get back to, if you haven't seen this before, I'll explain why this is a negative parameter here. But first, let me state the key theorem that was the analog of a theorem we saw for the oriented Brauer category and the general linear group. If K is an infinite field of characteristic not equal to 2, then both of these functors are full. The one to orthogonal modules for the orthogonal group, and this one for modules to the symplectic group. Right? So this is the analog of the theorem we had that the functor from the oriented Brauer category to modules for the general linear group was full. So when you do the orthogonal and symplectic series, you need this Brauer category. And that's because the natural module is self-dual. So it's the Brauer category instead of the oriented Brauer category. The proof I won't go through this time because it's very similar to the proof we did for the oriented case. You do this same trick to reduce it to a statement about endomorphism algebras. And then it reduces to this classic result of Brauer that the Brauer algebra surjects onto endomorphism algebras of the tensor powers of this natural module. So the analog of Schur-Val duality, but for the orthogonal and symplectic groups. The same type of proof. But let's go to this case, this issue that because we got this negative parameter, what this is saying is that this natural module has negative categorical dimension. So this is a case where categorical dimension doesn't quite correspond with usual dimension because the categorical dimension is negative. Well, why is that the case? At least where do you see that it's negative? Well, if we look at where this bubble is sent, well, it's a cup composed with a cap. So the cup sent the bubble to, remember that the cap did this, sent it to V tensor V check. And then that was the cup. And then the cap applied your bilinear form. So what you get is this sum here. But that check meant left dual, not right dual. So we need to flip it so that the dual is on the left. But this is a skew symmetric form. So when we flip it to put the dual on the left, we pick up a minus sign. And now all of these V checks paired with V's are 1. And you have exactly 2D summands here, because we have 2D basis vectors. So you see you get minus 2D. So you see the categorical dimension is negative for the symplectic group. Now, if you're familiar at all with superalgebras and the super world, you should immediately start thinking, well, really, I can combine everything here. What I should really be doing is I should take a super vector space. So this is something that its even piece is m-dimensional and its odd piece is 2n dimensional. And we should let phi be a non-degenerate supersymmetric bilinear form. That means it's symmetric on the even part and skew symmetric on the odd part. And even and odd parts, it's symmetric on those. And then you have a monoidal functor you can check from the Brauer category at parameter m minus 2n, and that's the super dimension. The super dimension of a vector space, by definition, is the dimension of the even part minus the dimension of the odd part. And if you ever saw that and wondered why that's a natural thing to do, you can see that in the language of monoidal categories, that naturally is what corresponds to the categorical dimension. It's really the super dimension. Right? Because of this same fact, when you compute a bubble, you always pick up minus signs for odd parts. Right? That's why the super dimension is a natural thing. It's the categorical dimension. And your functor does the expected thing. It sends the generating object to the natural module. It sends crossing to flip, but now this is the super flip. It flips vectors, but you get a minus sign when you flip two odd vectors. So it's the standard symmetry that you have in the super world. And your cap is sent to this supersymmetric bilinear form, and your cup is sent to its dual, which I didn't write down, but it's the exact same formula as before. Yep.
So this is monoidal, not super monoidal.
This is a monoidal category, not a monoidal supercategory. That's a good point, because I'm about to discuss monoidal supercategories. And that's because even though we have a supergroup here, this category, by definition, I'm just taking even homomorphisms between modules. So this category of supermodules over this supergroup is actually a category and not a supercategory. So it's a usual category. And in fact, this functor, even in this more general setting, it's more general because you could take m to be 0 or n to be 0, and you get back the two functors I defined before. But even this more general one is full over the complex numbers. Okay, so you still have this nice property. You may then be tempted to go back to the oriented case and say, well, we could have done super there as well. And you could. You can replace the general linear group by the general linear supergroup, and you get a functor in the usual way. You basically don't have to change anything except the flip is now the super flip, and your parameter is the super dimension. It's m minus n. And again, this is full over the complex numbers. Any questions here?
Under which conditions the functor is essentially surjective, so we can identify the right-hand side.
Yeah.
Module category, the quotient.
That's a very good question. So in this super setup, it will not be essentially surjective. The representation theory of, if m and n are both non-zero, this is not even a semi-simple category. Things get more complicated in the super world. Yeah, even in the GLMN case as well. Yep.
How does looking at groups preserving split signature forms interact with this picture?
Also an excellent question, which I will say something about in a minute. So we're working over complex numbers, but if you go to the real numbers, then you have all these split signatures. That's very recent work that I'll talk about at the conference next week, but I'll say a few words here as well. Other questions?
When is this functor injected?
Good question. There is a condition, I don't remember off the top of my head. So this fullness was proved by Gus Lair, Ruibing Zhang, and Deline. And they also, I believe in that paper, give some condition when it's injective. It's some relation between the m, the n, and the number of tensor powers. I forget the condition off the top of my head. Some inequality. Yeah.
So in the oriented case, it's also full when k equals c.
That's right. Yeah. But not essentially surjective. So the modules in the image are what are sometimes called the tensor modules that are summands of powers of the natural and its dual. Okay, so I wanted to conclude this course with some very brief remarks about how you can go even further. So once you start realizing that maybe the most appropriate setting is to work in the super world, then you back up and say, well, okay, maybe from the very beginning I should have done everything super, even for the categories themselves. And there's a theory of monoidal supercategories, which is not that different from the theory of monoidal categories that we discussed. It's really not that much more difficult. There's just one minor thing. Your morphism spaces are now vector superspaces. So your diagrams can be odd or even, or linear combinations of odd and even things. And the only real thing that changes in practice is that your interchange law picks up a sign. So now when you move two morphisms past each other via this kind of rectilinear isotopy, if they're both odd, you pick up a sign. That's really the only difference. So you can still manipulate all these string diagrams. You just have to be careful when things change height that you might pick up a sign. But now you start thinking, well, we try to examine all the possibilities for how symmetry and duality can interact. So an object can have a dual that's different. It can have a dual that's the same. That's how we got the oriented Brauer and the Brauer. But now that you go to this super world, you realize there are a few other possibilities, because an object can be isomorphic not to its dual, but to the parity shift of its dual, where you flip the parities of everything. So that's something that only exists in the superworld. And if you do that, and you repeat how you would deduce the Brauer category, but under this motivation that you want a universal category where the object is isomorphic to the parity shift of its dual, you get what's called the paraplectic Brauer category. So this has one generating object, which we use the same symbol to denote. It's still got crossings, caps, and cups, so same generators as the Brauer category. And in fact, the relations look almost the same except for this sign here. And the fact that the cups and caps are odd now. So anytime a cap and a cup change height in a diagram, you pick up a sign. So all these arguments that we were doing, you can do the same type of arguments. You just have to be careful when you're manipulating things. If cups and caps change height, you get a sign. And if you use this zigzag relation in that orientation, you pick up a sign. But all the proofs go through up to these signs you have to take care of. And then you can show things like crossing slide over cups. But this one, when you put a crossing on the cup, you get a minus sign. When you put it under a cap, you don't. Another interesting thing is you can show that the categorical dimension of the generating object is 0. It's a very easy proof. This is equal to the figure 8 by using this relation where I change the cap to a crossed cap. But now I use this relation and change the cross cup to a negative cup. And so I get that the bubble is negative the bubble. So the categorical dimension is 0. This actually shouldn't surprise you because we're talking about an object that's isomorphic to the parity shift of its dual, which means its odd dimension and even dimension are the same. So the super dimension is 0. So this is the free symmetric monoidal category on a super symmetrically odd self-dual object. So dual to its own parity shift. And it has a universal property. Sorry, that's the universal property, but then that implies some connection to representation theory. If you take the paraplectic supergroup, which by definition is the automorphism supergroup of the space CNN that preserves a non-degenerate, supersymmetric, odd bilinear form, right? Then by the universal property, you've got a functor from this paraplectic Brauer category to the category of supermodules over that paraplectic supergroup. Notice one thing that's sort of interesting here. The paraplectic Brauer category does not see this n anywhere because the categorical dimension is always 0. It's the same category that goes to all of these, and it's full over the complex numbers. So you might think, well, how can that be? That means all the representation theory of all these is the same. Well, it's not. It's because the kernel of these functors depends on n. So it's the same functor is full onto all of these categories, but has different kernels. Oh, by the way, so then you might also ask, can I do the same thing for the oriented Brauer category? So you could have that it's dual, you add in the dual and have your cups and caps be odd. But in that situation, you can do a little trick, which is you can parity shift your down arrow and turn them even again. You can't do that in the self-dual case because it's dual to its parity shift of itself. So you can't just change the parity of one of them. But for oriented Brauer category, you could. So there's no oriented paraplectic Brauer category, or it's at least isomorphic to the usual oriented Brauer category. So there's one other thing you can do when you're in the super world. Remember this assumption we made that the endomorphism algebra of our generating object, say let's call it V, is the ground field. And I justified that by saying you should think of this as a simple object. And so Schur's lemma tells you that the endomorphism algebra is just the ground field if your field is algebraically closed. However, in the super world, even if you work with complex numbers, Schur's lemma tells you there are two possibilities, because what Schur's lemma really tells you is that the endomorphism algebra is a division superalgebra. Right? Every non-zero thing is invertible. And over an algebraically closed field, the only finite dimensional division algebras are the field itself. But in the super world, that's not the case. You've got the complex numbers, and you've got this two-dimensional Clifford superalgebra, which is complex numbers with an odd generator that squares to -1. So there are two complex division superalgebras. And so you could think, well, what if I want a universal category where my generating object has endomorphism algebra that's this Clifford superalgebra? And then you get the oriented Brauer-Clifford supercategory. So the only difference is we take our usual oriented Brauer category, and we have to add on some extra generator that corresponds to this odd element that squares to -1. So we take one extra endomorphism of our generating object, which we denote by a dot. It's odd, right? So it's an odd morphism, and it squares to -1, right? So I'm just forcing the endomorphism algebra of up arrow to be this Clifford superalgebra by adding on this odd generator that squares to -1. And it slides through the crossing, and we want this bubble to be 0. The bubble with a dot to be 0. And you can show that in this category as well, the categorical dimension is 0. For similar reason, well, slightly different reason. If the endomorphism algebra is this Clifford superalgebra, then acting by that odd element epsilon gives you a symmetry that flips parity in your module. So that means the even and odd dimensions of this have to be the same again, and therefore the super dimension is 0. So this has a universal property. It's the free symmetric monoidal supercategory on an object whose endomorphism algebra is this Clifford superalgebra. Sometimes you might have seen the terminology of type Q module. It's type M if the endomorphism algebra is C. It's type Q if its endomorphism algebra is this Clifford algebra. And so that universal property gives you a functor to modules over what's called the isomeric or the queer supergroup. So by definition, it's the automorphism group of a module of dimension nn whose endomorphism algebra is this Clifford superalgebra.
What's the epsilon acting on that n representation?
Well, you're assuming its endomorphism algebra is CLC, so you've got an action of that epsilon, and that's how the dot acts.
Can we see it in the representation of Q of n? Can we see what that epsilon does?
Yeah, so what I would say is that this V, I would actually define it to be the Clifford algebra, n copies of the Clifford algebra, which as a vector space is isomorphic to Cn, and then your epsilon acts because it's here, right? And then you look at the group that commutes with that action, and that's the isomeric or queer supergroup. And again, just like we had for the paraplectic case, there's no n on the left-hand side. It's the same oriented Brauer-Clifford supercategory that surjects onto all the morphism spaces of all the isomeric supergroups, or their module categories. And it's just the kernel that depends on n. And then again, you might think, well, there should be an isomeric version of the unoriented Brauer category. But if you play around a bit, you can see that that category collapses to 0. You can do little diagrammatic tricks to show that everything collapses there. So there's no unoriented case where you've got these dots, it's odd dots that square to -1. Any questions on that? Now, I know people may not be so familiar with super stuff, in particular supergroups, but I want to give you a flavor of how this idea of symmetry and duality, there become more options when you go to the super world. And let me end with one thing that's related to the question about split signatures. Even when I said here, I worked over complex numbers in algebraically closed field. Now you might start thinking, what about other fields? For instance, real numbers. That's important to look at representation theory of groups over real numbers. And then you start with that assumption, well, what should the endomorphism algebra of my generating object be? Schur's lemma tells you it needs to be a division algebra in the non-super case, or a division superalgebra in the super case. And there's this remarkable fact that I didn't know until fairly recently, well, I knew the first one. There are exactly 3 division algebras over the real numbers. So those are, probably a lot of people knew this, the real numbers, the complex numbers, and the quaternions. In the super world, there are exactly 10 division superalgebras, right? So you get 10 versions of this oriented Brauer category where now your strands can carry little dots that are labeled by elements of a division superalgebra. And if you go to the unoriented case, you actually want your division superalgebra to admit an anti-involution, and then you only have 4 cases, because only 4 out of these 10 admit an anti-involution. So you get 4 flavors of the unoriented one and 10 flavors of the oriented one. And these are related to real supergroups, and you don't even need super for this to be interesting. So for instance, you could study representation theory of, the indefinite orthogonal groups. This is a real form of the complex one where you take p plus q. And so that would be one of these cases where you pick the corresponding division superalgebra. Or you can look at the unitary group. So the unitary group is this case where you take complex numbers. Your oriented Brauer category, the coefficients are real numbers, but your strands can carry complex numbers. And so that controls the representation theory of the unitary group. So you can study all of these real groups and real supergroups by looking at these various possibilities. So that's in fact what I'll talk about at the conference next week. It's a little teaser of that. So that's it for the course.